students, let us study vibrations in a string. Here we consider a string fixed between 2 points. 2 ends are fixed and the string is under tension. That tension, suppose it is T. T is the tension in the string, M is mass per unit length of the string. Then if we form wave on such string, then its velocity is given by velocity of wave in string is V is equal to under root T upon M. This point we have considered in the syllabus of 11th standard. Just you have to remember that equation V is equal to under root T upon M is the equation for velocity of wave on stretched string, and we have to consider that equation in the study of vibrations. Here vibrations produced in a string, different types of vibrations, different types of waves we have to study. Those waves of vibrations are called as modes of vibration on the string. So if here there is a stretched string, its length is L and it is disturbed at the middle, it is plucked at the middle, means it is vibrated perpendicular to the length of string. Then vibrations are produced along the string, and it is found that here the string takes the shape of a loop, or we observe loop on the string. Single loop is produced when the string is vibrated exactly at the center. So here there are 2 nodes, 2 nodes and 1 antinode. This type of vibration or stationary wave in which it vibrates, it is called as fundamental mode of vibration. This is the first mode, simplest mode. We write first, it is first mode of vibration, first way of vibration, but generally it is called as fundamental mode of vibration. Fundamental mode of vibration. Simple mode of vibration is the simplest mode of vibration in which single loop is produced, 2 nodes, 1 antinode is there. In this case, for the wave we write velocity is equal to V is equal to N into lambda. It can be also written as N is equal to V upon lambda, but V, we know V is equal to under root T upon M, where T is tension, M is mass per unit length. Now we have to rewrite the equation in terms of length. So here we know there is single loop, length of one loop is equal to lambda by 2. So we can write this whole length is equal to lambda divided by 2, means length of one loop is equal to L. So here N can be written as 1 by substituting lambda. Lambda is equal to twice L from figure, here as lambda is equal to twice L from figure. This is equation number 1. It is called as the fundamental frequency. because it is related to fundamental mode of vibration. Therefore, it is called as fundamental frequency of vibration. It is also called as fundamental tone. Only tone, fundamental tone. Simple mathematical steps are there. Now we go to the second point. Here, suppose this point is A. Related figure is figure A. Now the second disturbance we give in this way. Here, suppose at the center, if the string is clamped, there is clamp at the center. By any means it is given, so that this point cannot vibrate. But the string on both sides of this clamp can vibrate. We can vibrate it by giving oscillatory disturbance at the center of one segment. Here there are two segments. This is first segment, this one is second segment. Any one segment is disturbed in this way, means oscillatory disturbance is given to the center of this segment. Then here wave is formed, is incident wave. We show is incident wave. It travels in both the directions. We can give the points as usual. This is point A, left point is A, right fixed end is B. In first figure also we give the points like this. Now incident wave is formed by simply disturbing one segment. Then we know by the reflection of wave there is superposition of reflected wave and incident wave. Incident wave means the wave which we have produced, and reflected wave is the wave which is reflected from the fixed ends here. Such disturbance produce the stationary wave consisting of two loops. Here in the discussion, here there are two loops, and those are formed between three nodes, and two antinodes are in between the nodes. This mode of vibration is called as second mode of vibration. And for this mode, wavelength is different as well as frequency is different, but velocity of wave is same, because tension is same, mass per unit length is same, therefore velocity is same. We write V is equal to, considering frequency as n1 and wavelength as lambda 1, we write lambda n1 is equal to V upon lambda 1, and here 1 upon lambda 1, and substituting T upon m. We have to substitute T velocity as under root T upon m every time, because the string here we have to give the frequency in terms of T, m and L. Now for this lambda 1 we can substitute as from figure, as there are two loops, 2 into length of one loop. Length of one loop is lambda 1 by 2. Length of two loops is 2 into lambda 1 by 2. And this is the length. That length is constant, is L. So by cancelling 2 and 2, here L is equal to lambda 1 or lambda 1 is equal to L. Here lambda 1 is equal to L. So we substitute lambda 1 as L. And we can note here that N1 is equal to, by comparing with this equation number 1, here with equation number 2, we can write N1 is equal to twice N, because here in the denominator there is 2, here if it is multiplied by 2 divided by 2, we can write N1 is equal to twice N. This is equation number 3. As N means fundamental frequency is multiplied by 2, this frequency is called as, usually it is in terms of harmonic, it is called as second harmonic. And for the fundamental frequency, it is called as first harmonic. So different terms, different words are used to show the different frequencies. Now there is again number of modes of vibration. We take one more mode of vibration, that is in the point C. Same the arrangement of clamp we have to use here, but instead of single clamp here we use two clamps. This is first clamp, this one is second clamp. Clamp means it is simple one object which can be mounted on the wire, or it can take the wire, and if the vibrations are given to the string, that clamp portion, that clamp point does not vibrate. So this is the use of clamp here. You just remember that here the points are made in such a way that they cannot vibrate. Now here there are three segments, 1, 2 and 3. Any one of the segments is vibrated up and down, so that wave is produced on both the sides. It can travel on both the sides towards B as well as towards A, that is incident wave. From B it gets reflected and we get here 3 loops by in this arrangement. 3 segments produce 3 loops here. The wave vibrates, the string vibrates in such a way that there are 3 loops. Here once the string takes the form of loop, we cannot show here the string. Here in this case we write there are 3 loops, and those loops are formed between 4 nodes. This one is first, second, third and fourth. 4 nodes are there. 3 antinodes are there. We write 4 nodes, 3 antinodes, and this mode of vibration is third mode of vibration. Usually these modes of vibrations are used in music and especially in stringed instruments like guitar, violin, sitar. Such modes of vibrations are used to produce different frequencies. Now we are at the third point, which is third mode of vibration. Here waves consisting of 3 loops are there. It is also having different wavelength. That wavelength is now denoted by lambda 2. so that we can write in this case V is equal to N2 lambda 2. Lambda 2 is the wavelength, N2 is the frequency, so that we write N2 is equal to V upon lambda 2. And again further substitution gives us 1 upon lambda 2 under root T upon M. Now we have to substitute for lambda 2. Here lambda 2. Here 3 loops are there. Then lambda 2 by 2 is the length of one loop, but 3 loops are there, therefore we write 3 into lambda 2 by 2, and this length of 3 loops is equal to length of a string. Then lambda 2 can be equal to twice L upon 3. You have to take this point like this. If we substitute for lambda 2, it is twice L by 3. 3 can be written in the numerator. Here we adjust the relation. N2 is equal to 1 upon lambda 2 under root T upon M. Here under root T upon M as it is. Lambda 2 is twice L upon 3, but this 3 can be taken in numerator. So we get equation number 4. Now again N2 can be written in terms of this N. It can be N2 is equal to, N2 can be written as 3 into N. This is equation number 5, and it is called as third harmonic. Simple discussion is continued here. This is first harmonic. 1N is first harmonic, 2N is second harmonic, 3N is third harmonic. So for the third mode of vibration, we obtain the frequency N2. It is equal to 3 into N. It is called as third harmonic. Now if we go on writing such harmonics, then again we can form the fourth figure by having 3 clamps. Then it will consist of 4 loops. Then in the fifth mode it is 5 loops like this. We can continue it, but now for our discussion these 3 figures are sufficient. In the first mode amplitude is large, wavelength is lambda. In the second mode of vibration, amplitude is slightly smaller than the first one. In the third, again the amplitude is smaller than the second one. Amplitude, wavelength, frequency, all are different than the fundamental mode of vibration. Now, again we consider the term used for fundamental frequency. It is fundamental tone, first harmonic. This is also called as, it is numbered as first overtone. This is the point related to, it is fundamental tone. Already we have written fundamental tone. For the second harmonic, it is called as first overtone, and for the third harmonic it is called second overtone. The terms harmonics and overtones are used in case of the vibrations which produce stationary waves. If the waves are transverse or longitudinal, if there are number of modes of vibrations, number of harmonics are present, and harmonics are also called as overtones, but the numbering is different. In this case of stretched string, first harmonic is called as fundamental tone. Second harmonic is called as first overtone because numbering of overtones starts just after the fundamental frequency. Here this is the fundamental mode. So this equation is fundamental frequency. It is also called as fundamental tone. So try to write. Now we consider the second point in this vibration produced in a string. That point is laws of vibrating string. We have obtained one equation in the last discussion as n is equal to 1 upon twice L under root T upon M, which is representing fundamental frequency of vibrating string under tension. Tension is T in the string, M is mass per unit length, and we have discussed V is equal to under root T upon M. It is the velocity of transverse wave traveling along this string here. Now if we conclude for this equation by considering any two factors as constant, then relationship between two remaining quantities is known as law of vibrating string. It can be stated like this. So the first law of vibrating string, it is also called as law of length. Just we have to write those expressions here. Law of length. Here if we take the equation or the proportionality between n and l like this, n is inversely proportional to l if T is constant, M is constant. Then this conclusion from this equation, here we know that when T and M are kept constant, 2 is constant, then N is inversely proportional to length L. So N is inversely proportional to L if T and M are constant. In words, we say that here frequency of vibrating string is inversely proportional to length of vibrating string if tension and mass per unit length is constant. It can be written as N L is equal to constant if T and M constant. If mass per unit length and tension is constant, then this statement gives us first law of vibrating string. Again we draw the second conclusion. If L and M are kept constant, then N is directly proportional to square root T. Here we can write second law of vibrating string. It is called as law of tension. How can we write that conclusion or that law? It is N is directly proportional to under root T if L and M constant. It can be written as N upon under root T. This ratio is constant if L and M are constant. So this is simple statement we make that frequency of vibrating string is directly proportional to square root of tension given to the string if length of string is held constant, mass per unit length of string is kept constant, means string is not changed, For a given length, n is directly proportional to square root t. Now the third law you can also write, that is third law of vibrating string. Third law of vibrating string. This is very simple to write. It is also called as law of mass per unit length, because we have to show the variation of n with m, mass per unit length. And you also can state it that n is inversely proportional to square root of m. Here L and T constant, or it can be written as n into under root m. It is equal to constant if this L and T are constant. So these are three statements we can write from the fundamental frequency of vibrations. So we have to consider the third law of vibrating string, and for the mass per unit length we can write m is mass per unit length, mass per unit length of string. It can be obtained mass of string divided by length of string. Simple. Mass of string is equal to volume of string multiplied by density divided by the length. Now volume of string, as the string is a wire, it is having cross sectional area pi r square, and its length you know it is equal to L. Then volume can be equal to pi r square into L. Suppose density of material is denoted by rho. Here we mention that rho, density of material of string. Then the formulation is simple here. It is just we have to write, substitute and then formulate. Length is there in denominator. We get mass per unit length as pi r square into rho. It is also called as linear density. So these deductions or this formulation we discuss here for the solving numericals as well as multiple choice question. This linear density of string. Now in the third law of vibrating string, if we take it as like this, by considering this equation also we can take this n is equal to 1 upon twice L under root t upon m. M can be substituted as pi r square into rho. If t and L are constant, we can say that n is inversely proportional to 1 upon r square, or n is inversely proportional to 1 upon r. But instead of saying r square, we call it as n is inversely proportional to r, because we can write it like this. Also n is inversely proportional to square root of rho. So in the third law of vibrating string we have written n is inversely proportional to square root of mass per unit length. In other words, we also say that if t and L are constant, n is inversely proportional to radius of string, as well as n is inversely proportional to square root of density of string. So these are two more conclusions and can be written for the solution of some numerical problems as well as MCQ. So various quantities, actually there are 4 quantities like P, M and L related with N, but these 2 more quantities we have to relate. This is the discussion for vibrations produced in the string and one point which is laws of vibrating strings. So today we stop here. Thank you.